Good afternoon, dear colleagues. My name is Boris Lapin and I am from Crimean Federal University Physical and Technical Institute. My report is called Propagation of Optical Vortices in Fiber Ring Resonators. What the fiber ring resonators are? They are all fiber devices which can be used at creation, for example, optical filters, sensors, frequency combs, gyroscopes, and so on. In despite of their honorable age, at the present time fiber resonators still attract attention of many researchers, both theorists and experimentalists. It should be noted that the last actively make various optical resonators in their laboratories. As is evident from my report's title, we have considered fiber ring resonators. They are known at least for 35 years, so what is the difference between our studies and the well-known ones? We have considered ring resonators based on multi-mode fibers. Why is this important? They can affect not only a fundamental mode but also higher order ones. Therefore, fiber ring resonators can potentially control very useful fields, optical vortices, which have a wide field of applications, for example, in informational technologies. Now, let me remember what the ring resonator is. As is seen from the figure A, the ring resonator consists of a bus fiber to which a fiber ring is coupled via evanescent fields. The length of the coupling zone is S, and the length of the ring is S plus D. An equivalent scheme of the ring resonator is shown in figure B. One can see that a ring resonator is a fiber coupler which consists of U and L fibers, where a fiber, for example U, is self-closed by a curved piece of fiber. Then the port I of the L fiber becomes the input of the resonator and the port O becomes the output of it. The cross-section of the coupler is shown in figure C. As is seen, two cores with round cross-sections and refractive index NCO are immersed into an infinite cladding with refractive index NQ. The distance between the cores is big lambda and less than course radius. Main parameters of the ring resonator are length of the coupling zone, input power redistribution between coupled cars at the output end of the coupler, length d of the curved segment, and refractive indexes of cores and cladding. We suppose that incoming field is an optical vortex L, and output ones are L with power T plus and minus L, where L more than 1 is the topological charge of the optical vortex. It should be noted that the model of the ring resonator we built is full vector. For simulation, we take the following values of the main parameters. You can see them on the slide. Also, it should be noted that the method we used is transfer matrix formulas and matching fields on the boundaries. You can see our paper Topological resonances, super efficient orbital angular momentum control and spin-orbit interaction enhancement in fiber loop resonators. So what is the result? First, consider the case of excitation of the ring resonator by the optical vortex with a topological charge more than unit. Then, as follows from figure A, tuning of the ring's length d allows one to invert the sign of topological charge of the outgoing field. The same situation is observed when the ring resonator is excited by the optical vortex with the topological charge minus L. This is not a sole role of the ring resonator. If one could calculate the difference between the phases of the outgoing fields, then he will see that at the length dA the ring resonator operates like a quantum logic X gate, while at the length dB like a quantum Y gate. Such a property allows one to use ring resonators as a potential components of the quantum computers. Another property of the ring resonator is possibility to continuously control the orbital angular momentum of the outgoing field by the changing of the ring's length d. This can be useful at micro-manipulations operations with microparticles. The last properties of the ring resonator we found are possibility to serve as a comb filters and a significantly increase group delay time. Indeed, as is seen from the figure on this slide, the power of the outgoing vortex with the topological charge coinciding with the topological charge of the incoming vortex can be described by a comb. Spike of this comb corresponds to a significant group time delay, which can reach 5 nanoseconds. In conclusion, I can say the following. The optical fiber ring resonators on the basis of multimode fibers allows, first, inversion of topological charge of optical vortices, second, controlling of orbital angular momentum, third, creation of optical quantum logic gates, fourth, making of optical comb filters and time delay lines. This work was made with my co-authors Konstantin Alexeyev, Elena Barshak, Maxim Yevorsky and Dmitry Vikulin. Thank you for your attention.